If you think 3i Atlas is the scary one, you're looking in the wrong direction. Hit subscribe right now because the real close call is already booked on the calendar. On April 13, 2029, an asteroid named Apophis will slide past Earth so close it will be inside the distance where many satellites live. And yes, you'll be able to see it with your own eyes from parts of Europe, Africa, and Asia, like a moving star that doesn't belong. Now, before your brain goes straight to disaster movie mode, let me say the calm part up front. NASA has ruled out an impact in 2029, and for at least the next 100 years. So no, this is not a "we are doomed" video. But here's why. This is still far scarier than most space stories. Because the scary part is not a guaranteed hit. The scary part is how close it comes, how much we still have to predict, and how small forces can bend a future we can't fully see yet. Apophis is named after the Egyptian god of chaos, which feels like the universe trolling us. But the name fits because this asteroid has been a chaos machine since day one. It was discovered in 2004, and for a moment, the early numbers made it look like it had a real chance of impacting Earth later on. People panicked, headlines went wild, and then the science tightened up, and the danger got ruled out. That's how it usually goes. But Apophis never stopped being important, because it sits in a special category, big enough to matter, close enough to study, and famous enough to become a test of whether humans can stay calm while the sky does something dramatic. Apophis is roughly 340 meters across. That's not a pebble. That's a skyscraper laid on its side. If you put it in a city, you wouldn't call it small. You'd call the police. And in 2029, it comes within about 32,000 kilometers above Earth's surface. That's the distance that makes you sit up. Not because it's hitting us, because it's close enough that Earth's gravity will tug on it hard. And when Earth tugs hard, you don't just get a flyby, you get a reshaping. This is the part most people miss. We think of asteroids like bullets. They either miss or hit. But in space, there's a third option. They pass close and get changed. Their orbit gets tweaked, their spin can change, their surface can crack, dust can lift, boulders can shift. If it's a rubble pile, the whole body can settle into a slightly new shape, like a bag of rocks being gently shaken. That's why scientists are excited, even while the rest of the world is just hearing close approach and sweating. To researchers at NASA Jet Propulsion Laboratory in California and the Center for Near-Earth Object Studies, this is like the perfect classroom lesson delivered by the universe. A huge object, a safe pass, a front row seat to gravity doing its thing. And because it's close, the world's best telescopes are going to be watching. The European Southern Observatory will have eyes on it. Keck Observatory in Hawaii will be able to measure how its surface reflects light. Radar teams will try to map its shape and motion with insane precision. Even old Arecibo legacy data matters here, because the history of radar observation is what helped make asteroid tracking so sharp in the first place. And if you want a crazy thought, here it is. A lot of the most important science about Apophis won't come from one giant dramatic discovery. It'll come from boring measurements that stack like bricks, tiny changes in brightness, subtle shifts in timing, a slight drift in where it appears against the stars. This is why NASA-style stories sound calm, but they're actually high tension. Because the entire game is, can we measure small changes fast enough? And can we predict what those small changes do years from now? Now here's the twist that makes this video worth your time. Apophis is not the main threat because of 2029. Apophis is the main lesson because of what 2029 teaches us about the next ones. There are millions of rocks out there. Most are harmless. Some are not. And many are the kind you don't see until they are already close. So this story is not just about Apophis. It's about planetary defense. That phrase sounds like a superhero job, but it's real. NASA has a Planetary Defense Coordination Office. There are international groups that run what-if drills. Because if a real threat shows up, there's no time to argue on social media about whether it's fake. You need a plan. You need a phone list. You need to know who does what. And you need to know what tools actually work. So let's slow down and make it simple. An asteroid threat has 3 parts. Find it. Track it. If necessary, move it. Finding is the hard part, because space is huge and asteroids are dark. Most are basically flying lumps of charcoal. Tracking is also hard, because prediction is not just one line drawn in a notebook. It's math plus physics plus time. And moving it is hard because you can't push a mountain with your hands. You need technology and you need time. Time is the real weapon. If you find a threat 10 years early, you can nudge it gently and win. If you find it 6 months early, you start sweating. If you find it 2 weeks early, you're not doing Hollywood plans. You're doing emergency plans. So the first big point in this story is early detection. And that's where the modern era is changing fast, because we now have wide field survey telescopes scanning the sky almost every night. Projects like Pan-STARRS and the Atlas Survey Network and the Catalina Sky Survey have made it much harder for big objects to sneak up on us. And it's about to level up again. The Vera Rubin Observatory is coming online to do something close to a miracle. Scan huge parts of the sky again and again, building a time lapse of the universe. That's not just for pretty galaxy pictures. That's for moving dots. That's for near-Earth objects that used to hide in the darkness. Now add artificial intelligence. This is where people get confused. So let's keep it real. AI is not a magic alien detector. AI is a turbo assistant. It helps sort mountains of data. It finds patterns humans would miss because humans get tired. Imagine watching a stadium full of people and trying to spot one person waving. Now imagine doing it every night for years. That's what sky surveys are like. So AI helps. It flags moving objects. It helps match observations from different nights. It helps calculate better orbits faster. It does not predict the future like a wizard. It does the heavy lifting that frees scientists to do the thinking. And Apophis is the perfect example of why orbit prediction is both beautiful and scary. Because even when you know an object will miss, you still want to know exactly how it misses. Why? Because near misses can become future risks if certain tiny conditions line up. This is where we talk about the idea that sounds like a video game secret level: keyholes. A gravitational keyhole is a tiny region in space during a close flyby. If an asteroid passes through that tiny region, Earth's gravity can bend its orbit in a way that lines it up for a future impact years later. It's not magic. It's geometry plus timing. Think of it like a moving walkway at the airport. If you step on the walkway at the right spot, you exit at a different gate. If you step on it at the wrong spot, you miss your connection. Earth's gravity is the walkway. The keyhole is the right spot. And the future orbit is the different gate. Now, for Apophis, NASA has done the deep work. They used lots of optical tracking and radar measurements to shrink the uncertainty. That's how they were able to say, with confidence, no impact risk for at least 100 years. But here's what keeps planetary defense people awake anyway. Not Apophis. The general rule: the universe keeps sending rocks, and rocks are influenced by small forces. Which brings us to the quiet villain in the story, the Yarkovsky effect. This one is so sneaky, it sounds fake, but it's real. Sunlight hits an asteroid and warms it. Then, the asteroid re-radiates that heat back into space. That heat leaving the surface acts like a tiny push, like a slow, invisible engine. It's small, but over years and decades, small pushes become big drifts. It's like drifting on a canoe in a river. You don't feel the current at first, then you look up and realize you're far from where you started. So when scientists say, we ruled out impact, they mean with the best data we have and the best models we have. And when they keep watching anyway, they mean we never stop refining. Because the job is not just being right today. The job is being right years from now. Now let's talk about the 2029 flyby. Like, you are gonna be there because you are. On that day, Apophis will move fast across the sky. It won't sit still like a normal star. It will sweep like a silent drone. Except it's a mountain. That's the creepy part. The quiet. It's not roaring. It's not glowing. It's not exploding. It's just there, moving. And a lot of people will look up and feel something in their chest. Not because they think it'll hit, but because it's the first time in their life the sky will feel close. Because this is not the moon. This is not a planet. This is a piece of raw space passing through our neighborhood. Now here's where we turn the story into a serious news report, not a panic video. We ask the real question. What happens to Apophis during the flyby? Does it spin differently after? Do we see surface shedding? Do we see dust? Do we see changes in its light curve, which is just the way its brightness flickers as it rotates? Because those changes tell us what it's made of. A solid rock behaves differently than a loose pile. And if Apophis teaches us anything, it teaches us what an Earth-close pass can do to a big object. That matters for the next time the rock is not safe. Now, people always ask, can we stop an asteroid? Yes, sometimes, but it depends on time, size, and what it's made of. We've already done a real test of deflection. NASA's DART mission slammed into a small asteroid moon called Dimorphos, and it changed its orbit. Not by a tiny second, by tens of minutes. That was the first time humans changed the motion of a natural object in space on purpose. That is a major moment in human history that most people still don't appreciate. But here's the honest part. DART is not a one-button save Earth system. It's one tool, and it works best when you have time. Other options exist too. A kinetic impactor is basically a cosmic tackle. A gravity tractor is weirder. You park a spacecraft near the asteroid and let gravity slowly tug it over time. No touching, just pulling with mass. That's slow, but it's gentle. And yes, there's the nuclear option people whisper about. Not as an explosion that shatters the asteroid like a movie, but as a way to deliver energy in a controlled way to change its path. That's complicated, politically messy, and not a first choice. But it's part of the toolbox discussion because planet safety is a serious topic. Now, let's deal with the conspiracy crowd for a second, because every big space event pulls them in like moths to a streetlight. You'll hear people say NASA is hiding something. You'll hear people say Apophis is a cover story. You'll hear people say it's a weapon. Let me tell you the truth. The easiest way to build trust is not to shout people down. It's to explain uncertainty clearly. Science does not claim perfection. It claims process. You show your measurements. You show your error bars. You show your updates. You tell people what you know and what you don't. And you keep watching. That's why Apophis matters as a public event. It's a chance for the whole world to watch how real science handles a scary sounding situation without turning it into a circus. Now, let's zoom out for a moment, because Apophis is the headline, but the deeper story is the era we're entering. We are leaving the "we hope we notice threats" era. We are entering the "we build systems to notice threats" era. That's a big change, and it's happening because astronomy is getting faster, smarter, and more automated. The same AI methods helping track near-Earth objects are also used in other parts of space science. They help detect fast radio bursts. They help sort telescope images. They help catch weird transient events that flare and vanish. And while that's happening, NASA and other agencies are launching missions designed to map the universe in new ways. For example, the SphereX mission is mapping the sky in infrared in a way that helps us understand cosmic structure and also helps us trace where water and organic molecules show up in space. That might sound far from asteroids, but it's part of the same story. We are building a planet that watches the sky. And when a planet watches the sky, it stops being a passive target. It becomes a participant. Now, let's bring it back down to Earth, because we still haven't answered the title the way your brain wants it answered. An object far scarier than 3i Atlas is racing toward Earth. What is it? It's Apophis, not because it's going to hit in 2029, but because it shows us what a real near miss looks like and how tight the margins can get. And it also teaches an uncomfortable truth. The biggest risk is not the famous one you've heard about. The biggest risk is the one you haven't heard about yet. The ones still out there that are smaller, darker, and harder to detect because they come from the direction of the sun, where telescopes struggle. That's why planetary defense is a forever job. Now, I want you to picture a simple scene. A team at NASA Jet Propulsion Laboratory has a big screen showing Earth, a line showing Apophis, and a cloud showing uncertainty. At first, that cloud is huge. Then, with more observations, it shrinks. That shrink is the difference between fear and control. Because control is not power. Control is knowledge. Now imagine a different object in the future. Same screen, same Earth, same uncertainty cloud. But this time, the cloud doesn't shrink fast enough. That is the moment when the whole planetary defense toolbox matters. And that's why this story is not just about a flyby. It's a rehearsal. Now let's get practical and a little personal, because this part makes the viewer feel included, not just informed. What should you do about Apophis? You don't need to buy supplies. You don't need to panic. You don't need to spread doom posts. You do something better. You pay attention. You learn the basics. You treat this like the world's biggest science lesson in public. Because when the real threat shows up one day, and one day it will, the difference between chaos and calm will be whether the public understands what scientists are saying. Now, we're going to keep going and dig into the most interesting and most underappreciated part of the Apophis story. What Earth's gravity can do to an asteroid's body during a close flyby. Not just its orbit, its body, its spin, its surface, because if Apophis sheds dust, or shifts boulders, or changes its spin state, that will tell us exactly how fragile or solid it really is. And that will feed directly into one big question. If we ever had to move a similar object away from Earth, would a dart-style hit behave cleanly, or would it behave like hitting a pile of gravel? That's where the fear becomes real. Not fear of 2029. Fear of how complicated a real deflection could be if we wait too long. Now, about that blueprint for survival, the wild thing is, Earth doesn't just let Apophis pass. Earth grabs it, not like a hand, like gravity. And gravity is sneaky. It doesn't need to touch you to change you. When Apophis comes in close, it will feel Earth's pull harder on the near side than the far side. That difference is called tidal force. Same reason the moon pulls our oceans into tides. But an asteroid isn't water. It's rock, dust, and sometimes a loose pile of broken pieces held together by weak gravity, like a clump of rubble with pride. So the big question is simple. Is Apophis a solid chunk, or is it a pile that only looks solid because it's holding itself together? If it's more like a pile, the flyby can make it shift. Small landslides, dust lifting, boulders rolling, the surface rearranging itself like a shelf shaking during a small earthquake. And if that happens, it matters for two reasons. One, it tells us what Apophis is truly made of. Two, it changes how we would ever try to stop a similar asteroid in the future. Because there's a huge difference between pushing a brick and pushing a bag of gravel. You hit a brick, the brick moves. You hit gravel, the gravel absorbs the hit, throws dust, and you might not get the clean push you planned. That's why people at NASA JPL care about more than just the orbit line. They care about the body, spin rate, wobble, shape, surface texture, all of it. And the way they read that is not by touching it, it's by watching how it flashes. As Apophis spins, it reflects sunlight differently. Bright, dim, bright, dim. That pattern is called a light curve. It's like a heartbeat. If the heartbeat changes after the flyby, it means something physical changed. A new wobble, a different spin speed, a shifted surface. And once you notice that, you start asking the next scary question. If Earth can change an asteroid by just pulling on it, what would a deflection mission do? Because people love to imagine deflection like this. We see a rock coming, we punch it. It moves away. Easy. But space isn't a boxing ring. Space is a physics exam. NASA proved with DART that we can change an asteroid's orbit. That's real. That's historic. But DART also showed something people forget. When you hit an asteroid, you don't just push it. You can kick off a spray of debris, like a cosmic shotgun blast of dust and rocks. That debris adds extra push, like a little rocket exhaust. That means the inside and the surface matter. A lot. Now, here's where Apophis becomes the cleanest classroom example ever. We get to watch a big asteroid experience, a gravity stress test in front of the whole planet, safely. And the whole world will be watching. Ground telescopes, radar, space telescopes, university teams, even amateurs with good gear. And when you combine everyone's data, you get a before and after story that's hard to fake. This is also where AI actually earns its keep without being hyped like magic. Because during the flyby, the sky will be full of observations. Thousands, maybe millions of data points when you include surveys. AI helps with sorting, matching, and tracking. It helps confirm that the dot people are seeing is the same dot. It helps detect small drifts. It helps spot changes in brightness patterns that a human might miss because it's 3 in the morning and your eyes are cooked. But the important thing to tell your audience is this: AI is not the judge. AI is the flashlight. Humans still decide what the flashlight is showing. Now, let's talk about the truly scary idea that keeps scientists humble. Even when you rule out impact in 2029, the future is always a math problem with tiny errors. That's not a flaw of science. That's reality. Because long-term prediction is sensitive. A tiny push today can become a big miss or a big danger decades later, depending on timing. And space has tiny pushes everywhere. Sunlight heating and cooling the surface can slowly drift an asteroid over time. That's the Yarkovsky effect, the invisible nudge that can matter over years. A small change in spin can change how that thermal push acts. A tiny surface shift can change how it absorbs heat. So the flyby isn't just a close pass. It's an event that can change how the asteroid behaves afterward. And that's why the phrase "ruled out" always comes with a quiet second sentence in the science world. Ruled out based on current measurements. So the goal isn't to be scared. The goal is to measure so well that fear has nowhere to hide. Now, let's tackle a question regular people always ask, and it's a fair one. If Apophis is passing closer than many satellites, why aren't we worried it will crash into a satellite and cause chaos? The simple answer is space is big, even close to Earth. Satellites are tiny compared to the space they live in. The chance of a direct hit is low, but scientists will still track it carefully because low is not the same as zero. And this is exactly the kind of week where you don't want surprises. And here's another question people ask. If we can see it with our eyes, why can't we just track it easily and forever? Because seeing it is not the same as measuring it precisely. Your eyes can spot a moving light. They can't measure distance and speed to the level needed for future orbit prediction. That's why radar is a big deal. Radar can give shape, rotation, and distance changes with crazy accuracy. We don't have Arecibo anymore, but the legacy of what it taught the field still matters. And other radar systems like the Goldstone radar have been key for tracking near-Earth objects. This is also why teams will use every tool they can. Optical tracking from observatories, infrared tracking from space, because infrared helps reveal size and surface properties better than visible light alone. That's where missions like NASA's CNEOS help build the bigger map of near-Earth objects, and where newer systems are pushing toward earlier detection. Because again, time is the real weapon. Now, let's keep it human. Here's what Apophis really does to people. It forces you to feel two truths at once. Truth one, Earth is protected by luck more often than we admit. Space is huge, and most rocks miss. Truth two, luck is not a plan. And this is the moment where the story gets bigger than Apophis. Because Apophis is a celebrity asteroid. We have time, we have warnings, we have eyes on it. The real danger is the shy asteroid, the dark one, the one coming from the direction of the sun where telescopes struggle, the one that doesn't trend until it's already close. That's why planetary defense isn't one mission or one press conference. It's a long job that never ends. International teams already treat it that way. There are global coordination groups that share impact risk info and run response plans, because if a real threat appears, it won't care about borders. And that leads to the most important emotional point of this whole video. Apophis is not a death clock. Apophis is a wake-up call you can see with your own eyes. A reminder that we live in a shooting gallery, and we're only safe because we've started watching the range. So the real question now is not, will Apophis hit? The real question is this: when the next one comes, the one we haven't named yet, will we see it early enough to do something calm and smart, or late enough that all we can do is watch? Because if Apophis teaches us anything, it's that the difference between panic and control is not courage, it's preparation. And the next thing we need to talk about is the moment people never think about. What happens if an asteroid doesn't aim at Earth itself, but aims at the space around Earth? The space where our satellites live, Because even a near miss can still punch our modern world in the face if it triggers a debris mess, a communications crisis, or a chain reaction we weren't ready for. Because here's the uncomfortable truth about modern life. We don't just live on Earth anymore. We live around Earth. Your phone, your bank app, your GPS, your weather forecast, your live football stream, even the time on some networks, all of it leans on machines floating above your head. Satellites are the invisible bones of the modern world. So when people hear asteroid, they picture a rock hitting the ground. But a near miss can still be a nightmare if it messes with the space environment we depend on. Not because Apophis is going to smash into a satellite like a bowling ball. The chance of a direct hit is tiny. The real risk is what happens when space gets crowded and one bad day starts a chain reaction. Space junk is already a problem. Old rocket stages, dead satellites, paint flakes, tiny bits moving so fast they can chip metal. NASA and ESA track a lot of it, but not everything. And the more stuff we put up there, the more fragile the system becomes. This is why you sometimes hear the phrase Kessler syndrome, which sounds like a villain, but is really just a bad scenario. One collision makes debris. Debris causes more collisions. More debris makes space harder to use. Now, Apophis is not bringing that scenario, but it is bringing something else. Attention. And attention is good because it forces the world to look at the bigger picture. This flyby is like a public safety drill, except the drill is a real asteroid that nobody ordered. And drills are where you find out if your plan is real or just vibes. So what do scientists do with an event like this? They don't just say it's safe and walk away. They use it to upgrade the system. They use it to test detection. They use it to test tracking. They use it to test communication. Because one day, the threat won't be a famous asteroid with years of warning. It'll be something we notice late. And that's when you need your machine to already be running. That's why NASA's Planetary Defense Coordination Office exists. That's why JPL has teams that live in orbit math. That's why there's international coordination through groups that share risk data, because this is one of those problems where being proud and isolated is just dumb. Now, let's talk about the part that makes ordinary people feel the fear properly, without turning it into a cartoon. The fear is not Apophis hits. The fear is we live in a world where a rock the size of a city block can pass closer than satellites, and most people don't even know that's possible. Because once you know that, you start realizing something. Earth is not a closed system. We're not in a sealed room. We're in a neighborhood with traffic. And space traffic does not ask permission. So the real question becomes, what can we actually do if we had to? And this is where I want you to feel the difference between science fiction and real engineering. A lot of people imagine deflection as one big heroic move, but real planetary defense is more like steering a shopping cart. If you push early, it turns easily. If you wait until the last second, you're slamming into shelves. That's why early detection is everything. And it's why the next generation of tools matters so much. The Vera Rubin Observatory will help discover moving objects because it scans the sky again and again. Space-based infrared surveys matter because dark asteroids are easier to spot when you look for their heat. NASA's CNEOS surveyor mission is designed for that exact job, finding near-Earth objects with infrared eyes, especially the ones that hide in the glare where ground telescopes struggle. So when someone says AI will save us, don't roll your eyes, but don't worship it either. AI helps us handle the flood of data. It helps us catch the dot before it becomes a headline. It helps us connect the dots between nights. It helps reduce the time between something is out there and we know its orbit. And prospal. And time is the whole game. Now let's put a realistic toolbox on the table, because your audience loves this part when it's explained cleanly. Option 1, kinetic impact. That's the DART idea. Hit the asteroid with a spacecraft at high speed. Change its path a little. The goal isn't to blow it up. The goal is to shift it so it misses Earth by a lot. Option 2, gravity tractor. This one is almost funny because it sounds too gentle. You park a heavy spacecraft near the asteroid. No touching, just gravity. Over time, the spacecraft's gravity tugs the asteroid slightly. It's slow, but it's controlled, and it doesn't risk breaking the asteroid apart. Option 3, surface push methods, like attaching something that changes how sunlight pushes it over time, or kicking off material in a controlled way. These are advanced ideas, but the principle is simple. Small forces, long time, big result. Option 4, nuclear option. This is the one people always jump to, and it's the one serious teams treat like a last resort. Not because it's taboo, but because it's complex. It's not boom and done. It's physics plus politics plus risk management, and here's the honest part nobody likes. All of these options depend on knowing what the asteroid is. Because a solid asteroid responds differently than a rubble pile. A fast spinner responds differently than a slow spinner. A weird shape responds differently than a roundish one. So planetary defense is not just how to move a rock. It's how to understand a rock. That's why missions like OSIRIS-REx mattered. That spacecraft went to asteroid Bennu, studied it up close, and brought samples back. Japan's Hayabusa and Hayabusa 2 missions did similar work. They taught us that asteroids are not simple. Some are basically bags of loose material with boulders on top. Some have jets of dust. Some have surfaces that behave like powder. That kind of knowledge is not trivia. That knowledge is survival homework. Now, this is the part where your story gets really gripping, because you take the viewer from space danger to human reaction. Apophis will be visible in parts of Africa. That means you'll have millions of people seeing it with their own eyes. And when that happens, 2 things will be true at the same time. The sky will look beautiful, and the internet will go insane. People will post fake claims, fake dates, fake trajectories, old photos labeled as new, videos of unrelated lights. And if your channel is doing this right, your video becomes a calm anchor, not a panic factory, because panic spreads faster than rocks. So you explain the difference between a close pass and a threat, and you teach one simple mental tool. Impact risk is about probability and energy, not emotion. A small object with a high chance matters. A big object with 0 chance is still interesting, but not a threat. And in this case, Apophis is interesting, historic, and useful, but not a 2029 impact threat. Now, here's where we sharpen the scarier than 3i Atlas angle without lying. 3i Atlas is a mystery story. Apophis is a reality story. Mysteries scare your imagination. Reality threatens your routine. Because with Apophis, you're not scared of aliens or weird signals. You're scared of the simple fact that the universe throws rocks and our civilization is built on glass. We built a world where small disruptions ripple into big problems. One major communications outage can throw everything off. One GPS problem can mess with transport and logistics. It doesn't have to be the end of the world to be a very bad month. So when planetary defense teams talk, they don't only talk about impact, they talk about risk management. Now, let's zoom out for a second, because your summary mentioned other cosmic threats. And this is where you can keep the viewer hooked by giving them perspective. Asteroids are the danger we can do something about. There are other dangers we can't. Supernova type events are rare and far, and not something you can deflect. Dark energy is a giant mystery, but it's not going to smack your city next Tuesday. Fast radio bursts are strange, but they're not a near-term threat to daily life. Apophis sits in that special category of threats where human action matters. And that's why it matters as a story, because it's one of the few cosmic dangers where we can actually say we can build a defense. Now, here's a key moment that will keep viewers locked in. The flyby itself is going to teach us something we've never been able to measure at this scale so clearly. How gravity changes an asteroid's spin state. If Apophis gets a measurable spin change, that tells us Earth's tidal forces can torque big objects in close passes. That also tells us something important about after effects. Because spin and surface changes affect the Yarkovsky effect over time, which affects long-term orbit drift. That's how a safe flyby becomes a real laboratory. And it's also where keyholes come back into the story. Keyholes are tiny, but their consequences can be huge. If you're watching carefully, you're not just watching where Apophis goes in 2029. You're watching whether the flyby changes the orbit in a way that changes future encounters. Now, again, In Apophis' case, the best current models say no impact risk for at least a century. That's the calm fact. But the deeper lesson is that keyholes are real, and we've seen keyhole discussions in other asteroid cases, where small uncertainties used to matter until better data removed the risk. That's why good communication matters. Not, don't worry. More like, here's what we know, here's why we know it, and here's what we're still measuring. Now, let's bring the viewer into the live newsroom feeling, because this is where the engagement spikes. In the weeks before the flyby, the tracking updates will tighten, the uncertainty cone will shrink, the predictions will become almost surgical. Different observatories will confirm each other. Teams connected to JPL will publish refined orbit solutions. ESO observations will contribute precision astrometry. Radar observations will refine distance and shape. Universities will run models. And there's a strange emotional moment that happens when the uncertainty shrinks. People don't get less scared. They get more focused because now it feels real. Now it's a date and a time, not a rumor. And that's why the title works. Because even though it's safe, it forces the viewer to face the fact that Earth has appointments with space. Now, there's one more point that ordinary people understand instantly, and it makes them click and watch longer. Apophis passes closer than satellites. That sentence alone makes it feel personal. So you take that and you turn it into a simple visual in words. You say, imagine every satellite as a small light in an invisible shell around Earth. Now imagine a mountain-sized rock threading through that shell, missing everything, slipping past and leaving Earth behind like nothing happened. That's what makes people uneasy. Not destruction, closeness. And if you keep that feeling, you can carry the audience into the next topic naturally. Because once you've accepted that closeness is real, you're ready for the big final question that hangs over everything. What would we do if the next one wasn't safe? Not the famous one, the unknown one, the one we spot late, the one that makes the uncertainty cone point at Earth before anyone has time to argue online. That's where planetary defense stops being a cool science topic and becomes a global leadership test. And there's only one way to pass that test. Build the system before you need it, because the universe doesn't care about last-minute plans. It cares about physics, and physics rewards preparation. And here's the part that almost nobody thinks about until it's too late. Even if we spot a dangerous asteroid early, the hard part isn't the movie moment where someone yells, "Launch the mission." The hard part is everything before that. Because planetary defense is basically 3 jobs that all have to work at the same time. One team is trying to find the object, another team is trying to lock down its orbit, and another team is trying to decide what kind of object it is, because the strategy depends on what it's made of. And the reason this gets messy is simple. Space does not give you perfect data. It gives you a few light dots on a few nights, and you have to build the rest of the story from math and patience. So when someone asks, how can NASA be sure? The honest answer is they don't rely on confidence. They rely on repeated measurement. That's why Apophis is so valuable. Because when it comes that close, measurement gets easier. The dot becomes brighter. The tracking becomes sharper. The uncertainty shrinks like a balloon losing air. And then we can answer questions we can't answer from far away. Like, is Apophis a single solid body or a rubble pile? Does it have a smooth surface or a rough one? Does it spin like a clean top or does it wobble like a shopping cart wheel that needs repair? These details matter because they affect how sunlight pushes it over time, and that affects the orbit. This is where you can tell your viewers something that sounds almost ridiculous, but is completely real. 2 asteroids can be the same size, in the same region of space, and still behave differently over decades because of tiny differences in rotation and surface heat. So if you ever wonder why scientists keep watching a safe asteroid, that's why. Now, here's the public-facing danger in all of this. When scientists speak carefully, some people hear weakness. When scientists say uncertainty, some people hear they don't know anything. We're 7, but uncertainty is not ignorance. Uncertainty is honesty. It's the difference between a person who says, I'm 100% sure, and a person who says, Here's the range, and here's why. In real danger situations, the honest person is the safer one. And that's what your video needs to communicate, without sounding like a lecture. Now, let's talk about the direction asteroids like to hide. This is the part that makes your viewers go, wait, what? The hardest ones to detect are the ones coming from near the direction of the Sunday. Because if you're looking into bright glare, you can miss dark objects. It's like trying to spot a black bird flying across the sun at noon. Your eyes are not built for that. That's why space-based infrared surveys are so important. Infrared is basically heat vision. Dark rocks still warm up and glow in infrared. So even if they look like nothing in visible light, they can show up as heat signatures. This is where modern planetary defense is heading. More sky coverage, more infrared detection, faster processing, better orbit solutions. And yes, more AI support. Not because AI is mystical, but because the data volume is insane. Now, there's another reason Apophis is a giant teaching moment. It's not only about detection, it's about communication. Because the world is gonna see it, and the world is gonna react. People will ask, why can I see it? And you say, it's not dangerous. So you explain the difference between close and collision. Close means it's passing nearby in space. Collision means its path intersects Earth's body. And those two things are not the same. Close is a near miss. Collision is a disaster. And Apophis is a near miss. Now, some people will still say, but what if NASA's wrong? That's where you bring the viewer back to the process. Apophis has been tracked for years. Its orbit is not a guess anymore. It's a refined solution based on lots of observations. That's why NASA can say no impact in 2029 and no impact threat for at least the next century. It's not a vibe, it's a measurement story. And the fun part is, the 2029 flyby will make that measurement story even stronger. Now, I want to shift the tone slightly, because this is where your audience stays for 2 hours. You give them a mental image that sticks. Picture the Earth as a tiny stage, light in the dark. Now picture Apophis as a dark object sliding through the edge of that light, briefly lit up like a passing car in a street lamp beam. For a few hours, it becomes bright enough that anyone can feel it. Then it goes back into the dark. That feeling that it was here and now it's gone is what makes people uneasy. It's not that it hit us, it's that it reminded us we're not alone out here. Now, let's put one more layer on the fear, but keep it responsible. There are levels of asteroid danger. A small one can explode in the atmosphere and cause serious damage in a region. A larger one can do much worse. Apophis sits in the category where you don't want to imagine impact, but you also don't need to, because it's not happening in 2029. So the smarter fear is not fear of Apophis. It's fear of being lazy. It's fear of learning the lesson and then forgetting it. Because after the flyby, the news cycle will move on. The internet will get bored. People will go back to normal. And that is exactly when the real work needs to keep going quietly. More surveys, more tracking, more missions, more drills, because the next one won't announce itself with a famous name and a public flyby. Now let's talk about the moment that separates a prepared planet from an unprepared planet. A keyhole moment. It's one of the most misunderstood ideas in space risk, so let's keep it street simple. During a close pass, there can be a tiny sweet spot in space. If the asteroid passes through that sweet spot, gravity bends its orbit in a way that sets up a future return that can be much more dangerous. If it misses that sweet spot, it returns safely or not at all. So tracking isn't just about one pass, it's about every pass, because one pass can reshape the future. Now, in Apophis's case, the major keyhole worries from the early years were removed as the orbit got refined. That's the good news. But the concept stays important because other asteroids can have real keyhole scenarios. And that's why JPL orbit teams obsess over precision. Because in a keyhole scenario, a change of a few hundred meters in the wrong direction can become a very different story years later. Now, here's the part where you keep the audience hooked by making it feel like a countdown, even though it's not a doom countdown. As we get closer to April 2029, this happens. The orbit gets more precise. The predictions tighten. The confidence grows. The public attention spikes. And the science gets richer. Because this is one of those rare events where the public and the research world are looking at the same sky at the same time. And you can use that. You can make this video feel like a guided mission, like the viewer is part of the observation campaign. Because they are. They're gonna see it with their own eyes. Now, there's one more angle in your summary we haven't leaned into yet, and it's powerful. This flyby is a global moment that can force governments to take planetary defense seriously. And let's be blunt, most governments only fund what the public can picture. Apophis is something the public can picture. A visible asteroid passing closer than satellites. That's the kind of thing that makes people ask, okay, so what's the plan for the next one? And once enough people ask that, the funding conversations change. Now, let's widen the lens for a second, because you mentioned cosmic context, and it helps your story feel bigger without losing the plot. There are threats we can't stop. There are mysteries we can't control. But asteroid defense is one of the few cosmic problems where human planning actually matters. It's like weather forecasting in the old days. At first, people didn't track storms. They just suffered them. Then we built systems. Now we can warn people. We can reduce harm. We can prepare. Asteroids are the same kind of problem, just on a different time scale. And the moment you say it like that, the fear turns into focus, because it means we're not helpless. We're just early in the learning curve. And that's what Apophis really is. A curve, a test, a reminder. Now let's go into the most dramatic, real-world part of this story without making things up. What happens if, during the flyby, we detect unexpected changes? A new wobble, a small surface event, a shift in rotation, a dust release. Anything that tells us Apophis is more fragile than we thought. Because if that happens, the conversation changes from cool flyby to serious case study. Not because Apophis becomes a threat, because it changes what we think about how asteroids behave when they pass close to Earth. And that changes how we plan deflection missions, because planning depends on realism. If the asteroid is fragile, you don't hit it like a hammer unless you know what that does. You might prefer a slow method. You might prefer a different approach. And that's exactly why scientists want this flyby so badly. It's like getting a free test run of the physics. Now, let's keep going. Because the next thing we need to tackle is the one question that makes this whole story feel personal. If Apophis is safe, why does it feel like a warning anyway? And the answer is simple, because it shows you the scale of the universe's near-miss game. And once you see that game up close, you don't forget it. Because your brain is wired to treat close like danger, even when the math says safe. It's the same feeling you get when a speeding car misses you by a meter. Nobody got hit, but your body still reacts like it almost happened. Your heart doesn't care about probability. Your heart cares about distance. And Apophis is the universe doing that to the whole planet. It's basically space leaning in close and saying, look, this is what a real near miss looks like. Now, here's where I want to be very clear with your viewers, because this is the line that separates a serious NASA-style story from a panic video. Apophis is not a secret. It's not hidden. It's not they don't want you to know. It's one of the most studied asteroids on Earth, precisely because it scared people early and then taught everyone a lesson about how fast bad information spreads when the numbers are still fresh. And that lesson is still useful today. Because when it comes to space threats, the real danger is not only the rock. The real danger is confusion. Confusion makes people distrust the process. Distrust makes people ignore real warnings later. So your job in this video is not to scare people into doom. It's to scare them into respect. Respect for how serious the problem is. Respect for how real the solution needs to be. Now, I'm gonna give your audience a simple mental model they can actually remember. When scientists track an asteroid, they don't say this line is the path. They say this is the most likely path, and this is the uncertainty. So they draw a line, and they also draw a cloud around that line. That cloud is not drama. That cloud is honesty. And when you keep observing, the cloud shrinks. That is what progress looks like, not a big speech, a shrinking cloud. Now, here's where the story becomes hopeful in a way that still feels intense. We are getting better at shrinking clouds faster because our sky watching system is getting sharper. The Vera Rubin Observatory will help find and track moving objects like never before. NASA's CNEOS surveyor is designed to spot heat signatures of asteroids that are hard to see in normal light. The European Space Agency has its own asteroid tracking and planetary defense work. And across universities, people are building better models and better software. Because this is one of the few problems where being smarter literally makes you safer. And here's a detail most viewers will love because it sounds like real spy work. Scientists don't just watch Apophis directly. They watch how its light changes. They watch how it reflects sunlight at different angles. They watch its color. They watch how fast it spins. They watch if its brightness pattern changes over time. Because those tiny clues tell you what the surface is like, smooth or rough, dusty or rocky, fresh or weathered. And those surface details affect the Yarkovsky effect, that slow sunlight push. So in a way, Apophis is like a suspect under a street lamp. It's not threatening you right now, but you're using the rare chance to see it clearly. Now, let's talk about why April 2029 is going to matter even after the asteroid is gone from view. Because after the flyby, the question becomes, what did Earth do to it? Did the spin change? Did the wobble change? Did anything shift on the surface? And the reason that matters is simple. If Earth can torque an asteroid just by passing near it, then close encounters across the solar system are not just travel routes, they are reshaping events. They are like invisible hands that can slowly rewrite orbits over time. And if you want your audience to feel the weight of that, give them a simple comparison. Earth is not just a target. Earth is a moving gravity machine, and gravity machines have consequences. Now, here's another angle that keeps viewers locked in, because it feels like you're revealing the hidden layer of the world. Even if Apophis is safe, the planetary defense system still has to be ready for the one that isn't. And the system has two enemies: late detection and slow decision making. Late detection is the universe's fault. Slow decisions are our fault. If an asteroid is found years ahead, we have options. If it's found late, our options shrink. And people hate hearing this, but it's true. A lot of the planetary defense battle is not rockets. It's paperwork and coordination. Because if an object is found on a risky path, you need global agreement fast. Who is responsible for sending what? Who pays? Who launches? Who shares data? Who talks to the public? Because if you don't get that right, the public message becomes chaos, and chaos makes people do stupid things. So the scary part isn't only the rock, it's whether we can act like a mature civilization when the sky demands it. Now, I want to bring in a real-world event that proves why this matters, without turning it into gore or fear-mongering. In 2013, a small asteroid exploded over Chelyabinsk in Russia. It wasn't Apophis-sized, it was much smaller, and it still injured people mostly from shattered glass and shockwaves, because nobody saw it coming. That's the lesson. You don't need a city killer to have a bad day, you just need a surprise. And surprises are what planetary defense is trying to eliminate. Now, your viewers might ask something like, okay, but why are you talking about other cosmic threats too? Because it gives perspective. Asteroids are the danger we can actually respond to. A rare giant explosion in deep space is terrifying, but you can't deflect it. Dark energy is mysterious, but you can't negotiate with it. Asteroids are different. Asteroids are one of the few big cosmic threats where planning actually changes the outcome. So when you talk about planetary defense, you're basically talking about a new kind of human power, not power over the universe, power over one problem, the problem of surprise. Now, let's shift into the part that feels like a news report, because this is where the pacing stays tight and the viewer feels like something is actively happening. In the months leading up to the flyby, watch what starts to appear. Updated orbit solutions, refined close approach numbers, better estimates of size and shape, new radar images, new light curve studies. And then, closer to the date, you will see something that always happens with big events. People will start spreading fake impact maps and fake timelines, so you say it clearly. A close approach is not an impact. A close approach is a measurement opportunity. And you can even give them a simple rule that saves them from fake posts. If a page is shouting certainty and refusing to show how they measured it, it's probably junk. Real science is calm because real science is checkable. Now, another piece of the story that makes people lean in is the idea of keyholes again, because it feels like fate and it's actually math. This is where you can make your audience feel smart. You tell them a keyhole is not a physical hole in space. It's a tiny region where timing and gravity line up in a specific way. If the asteroid passes through it, it gets set up for a future return that can be worse. If it misses, the story stays calm. And then you remind them. In this case, Apophis has been tracked so well that the scary keyhole story is not the Apophis story. The reason we talk about keyholes is because they are the hidden rule of close flybys. So Apophis is still a warning, but it's a warning about how the math works, not a warning that we're about to die. Now, we're gonna do something most space videos never do. We're gonna talk about what a real response would look like, step by step, if a future asteroid did show a meaningful risk. Not drama, process. Because process is what saves lives. First, you confirm multiple observatories, multiple teams, independent checks. Second, you refine radar if possible, infrared if possible, more nights of tracking, shrink the uncertainty. Third, you classify. Is it solid? Is it rubble? Is it spinning fast? Is it weird shaped? Fourth, you choose a method. If there is time, you choose a gentle push. If there is less time, you choose a stronger push. If there is very little time, you focus on emergency planning on Earth. And that last one is the part nobody likes to hear, but it's honest. Sometimes the best defense is not deflection. Sometimes it's warning and preparation. Because even if you can't move the rock, you can reduce harm by getting people out of danger zones. So planetary defense is not just space hardware, it's planning. Now, this is where you can use Apophis as the perfect practice run in the viewer's mind. Because Apophis will be close enough that we can measure it like never before without the pressure of it being an impact threat. So when that day comes and millions look up, you can frame it in one sentence that sticks. This is the day the world watches a real asteroid up close. Not to panic, but to learn how to protect the planet. And then you lean into the emotional hook that holds for long-form videos. We are the first generation that can see a threat coming and do something about it. Our ancestors could only pray. We can measure, we can plan, we can nudge rocks. That's not small, that's huge. But it only stays huge if we keep funding it, improving it, and taking it seriously after the headlines fade. And that brings us to the most important question you can leave hanging in your viewer's mind, the one that keeps them listening. When the next object appears, the one that is not a safe flyby, will we already have the system ready? Or will we start building it after the warning shows up? Because Apophis is giving us a free lesson, and the universe doesn't always give free lessons twice. And that right there is why Apophis is such a strange kind of fear. It's not screaming at you. It's not glowing green. It's not doing anything movie explains. It's just calmly reminding you that Earth lives in a real neighborhood. Now let's talk about what people will actually experience. Because this is where the story becomes real, in a way you can feel in your bones. On that April night in 2029, Apophis will look like a bright star that suddenly decides it has somewhere to be. It won't sit there. It will move. And if you've never seen something in the night sky move fast, you're gonna understand why ancient people made myths. Because your brain is built to trust the sky as the most stable thing in your life. When the sky moves, something in you goes, that's not supposed to happen. That's why this will be historic. Not because we're about to get hit, because millions of people will watch a real asteroid move across the sky with their own eyes. And the funny part is, the first wave of comments will probably be like, this is a plane. No, it's a UFO. No, it's Starlink. And somebody will say, my uncle warned me. And meanwhile, the science, people will be staring at numbers like proud parents watching their kid in a school play. Because for them, this is not a scary light in the sky. This is a rare chance to learn. Now, you're gonna hear the word close a lot, so let's pin it down in plain language. Apophis will pass closer to Earth than many satellites. That's true. But closer than satellites doesn't mean it's weaving between them like it's dodging traffic. Space is still huge. It's more like a football field with a few grains of rice floating around, and one marble passes through a wide open lane. Still a little spooky, but not a guaranteed crash. What matters more is that it passes close enough for Earth's gravity to pull hard. That pull is the whole show. Now, this is where you can hook people for a long time, because you give them a simple mystery that feels like a live experiment. What will Earth's gravity do to Apophis? Will its spin change? Will it start to wobble? Will its surface shift? Will it shed dust? If Apophis is more like a pile of rocks, this flyby could shake it like a jar. Not explode it, not break it in half, but shake it enough to move pieces. And the reason that's important is because it tells us something we can't learn any other way. If an asteroid can be rearranged by a close pass, then deflection missions need to account for that. Because you don't want your plan to be hit it here, and then the asteroid behaves like a bag of sand, and your push doesn't push the way you thought. This is why people at NASA Jet Propulsion Laboratory love boring details. Shape models, spin states, surface heat, light curves, all that boring stuff is the difference between a clean mission and a messy surprise. Now, let's talk about the biggest trap on the internet when Apophis gets close. The trap is this phrase: they said it won't hit, but they can't be sure. Here's the truth. They can't be sure about anything at infinite precision because reality has noise, but they can be sure enough to rule out an impact when the measurements are strong and repeated. And Apophis is one of the most repeatedly tracked asteroids we've ever had. That's why NASA has ruled out an impact in 2029 and for the next century. So if you want to be honest and scary at the same time, you say it like this: Apophis is not a threat in 2029. Apophis is a warning about how close can be, and how important early detection is for the next object. That's the grown-up version of fear. Now, there's another thing people don't realize until you tell them. Asteroid risk is not just about one day. It's about decades of tiny physics. That little sunlight push, the Yarkovsky effect, can slowly drift an asteroid over time. Tiny now, big later. And the flyby itself can change the asteroid's spin. And spin affects the Yarkovsky drift, which affects long-term orbit prediction. So the flyby is like a hinge in the story. Before the flyby, we know one kind of behavior. After the flyby, we measure again and see if Earth changed it. And the moment we see a measurable change, it becomes a case study that will live in textbooks. Now, zoom in on this part, because it's one of the most gripping ideas in planetary defense, and it doesn't need aliens to feel intense. Keyholes, tiny regions in space where a close flyby could set up a dangerous return later. In Apophis's case, the famous early worries about future impacts got removed as data improved. That's why it's not a threat for at least a century. But keyholes still matter as a concept because other asteroids do have that kind of sensitive future. So when the public sees Apophis and they feel that near-miss panic, you can guide them to the bigger point. If we can track Apophis this well, we can track others too. But only if we keep building the system. Because the system doesn't run on hope. It runs on telescopes and people and funding. Now, let's talk about the tools that make this possible. Because your viewers love how we do it. Stories. First, sky surveys. Ground-based telescope networks scan the sky nightly, finding moving dots. Then those dots get reported, confirmed, and linked across nights. That's where AI and automation help a lot. Not as a magic brain, but as a tireless worker that never gets sleepy. Then comes orbit math. That math is the quiet hero. It's not flashy, but it tells you where the object will be and where it won't be. JPL's orbit teams are famous for this kind of work because the stakes are high and the math needs to be clean. Then comes radar, when possible. Radar is like giving the asteroid a quick medical scan. You can measure distance more precisely. You can infer shape. You can see rotation. Then comes infrared. Infrared helps measure size and surface properties because it looks for heat. Dark rocks can hide invisible light, but they still warm up. That's why space-based infrared missions matter. It's one of the most practical upgrades we can make for planetary defense. And then comes the deflection toolbox. You already heard about DART. That was a real test, and it worked. And it didn't just change in orbit. It proved humans can do more than watch. It proved we can act. And follow-up missions and studies keep refining that knowledge, because one test isn't a full answer. It's a start. Now, there's another layer to your story that makes it feel modern and big. The same tools we use for asteroid defense are also being used to map the universe. For example, NASA missions that map the sky in infrared help us understand cosmic structure, dust, and even the distribution of molecules that matter for life's building blocks. So you can say something like this, and it hits hard. We're building eyes that can protect us and teach us at the same time. That's the best kind of science. Now, I want to bring it back to ordinary life for a second, because this is where your long-form script stays human. Imagine explaining Apophis to a friend who doesn't care about space. You wouldn't start with equations. You'd say, look, in 2029, a mountain-sized rock will pass closer than many satellites. You'll be able to see it, and it won't hit us. Then you'd say, but we should still pay attention, because it's like a fire drill for the whole planet. That's it. That's the story. And once you say it that way, people stop arguing and start listening. Now, here's another reason this is scarier than 3i Atlas. 3i Atlas is a mystery you can argue about. Apophis is a calendar event, a date you can point to, a thing the sky will do, whether you believe in it or not. That's why it sticks. Now, let's address the question that will pop up everywhere right around the flyby. If it's safe, why are scientists still talking about it like it's serious? Because the flyby is not just a show, it's data. And data is what makes the next crisis less scary. So the world will watch Apophis pass, and the research world will watch for changes. And if they find even small changes, the headline won't be, we're doomed. The headline will be, we learned something important. G's A2 hearted. Now, I want to lean into the emotional core of this story, because it's what keeps people listening for a long time. Apophis is a mirror. It shows us what kind of species we are. Do we panic and spread nonsense? Or do we learn and build? Do we treat science like a tool? Or do we treat it like a rumor? Because when the next object shows up, it won't care about our opinions. It will care about our preparation. And that leads us into the next layer of the story. The one most people don't even realize is part of planetary defense. What happens on Earth if a future object becomes a real risk? Not the space mission part, the human system part. The part where information can either save you or destroy you. So here's where the story stops being a cool space thing and turns into the moment that can change how humans behave. Because Apophis is not just a rock. It's a rehearsal for how fast panic can spread when the sky does something unusual. Picture it. It's the week of the flyby. The internet is loud. Someone posts a grainy clip with a fake caption that says, NASA changed the date. Another person posts a red line over a world map, like it's an impact path. Somebody else swears they heard a secret broadcast. And then 1,000 accounts repeat it, because fear is the easiest thing to sell. Now, at the exact same time, the real work is happening quietly. At NASA Jet Propulsion Laboratory, the orbit solution gets tighter and tighter. The uncertainty shrinks until it's almost boring. Observations from big facilities and university teams keep lining up. The numbers agree. And that contrast is the true climax of this story. The world is screaming, but the science gets calmer. Because the closer we get, the more we measure. And the more we measure, the less room there is for fantasy. Then the night comes. Apophis shows up, and it does the one thing that makes every human body pay attention. It moves, not like a star, not like a planet. It slides across the sky like something that shouldn't be able to happen. Like the universe broke its own rule for a few hours. People step outside and go quiet. Some laugh nervously, some whisper prayers, some record it with shaky hands. And in that moment, the planet shares one feeling together. Not doom, awe mixed with a small shot of fear, because it's close enough to feel personal. And then, while the world watches the light, the scientists watch the details. They watch its brightness pattern. They watch its rotation. They watch for a wobble. They watch for any surface change that would tell us what Earth's gravity just did to a real asteroid at close range. And if the measurements show even a slight change, a subtle shift in spin, or a new wobble, that becomes the moment. Not a crash, a lesson. A proof that close flybys can reshape these objects, and that planetary defense is not optional homework anymore. Because if Earth can tug an asteroid into a new spin state just by passing nearby, then the next time a real threat shows up, the plan can't be hit it and hope. The plan has to be smart, measured, timed early, built on real data from events like this. And here's the final punch that lands, because it's the honest truth. Apophis is not the thing that scares you because it will hit. Apophis is the thing that scares you because it proves how close can be and how fragile our comfort is. It's a reminder that we live under a sky that can surprise us. But it's also a reminder of something stronger. We are not helpless. We are the first generation that can see these objects coming, track them, understand them, and if we ever need to, move them. Not with magic, with math, telescopes, and decisions made early. So when Apophis fades back into the darkness after that flyby, it leaves behind two things: a memory you can't unsee, and a question you can't ignore. When the next object shows up, the one that isn't a safe near miss, will we already have the eyes and the tools ready? Or will we start building them after the warning arrives? Subscribe now, because the next video on your screen is where we break down the real planetary defense tools that could save Earth, and the one mistake that would make them fail.